So essentially, just starting out with basic probability. And I'm a terrible speller, so when I start spelling things wrong up here, don't worry about it. Just laugh to yourself. I don't need to know. It's fine. Okay, so first of all, what is probability? And I'm not a probability theorist or a statistician, but I'm going to go with this definition of probability. Essentially, probability is quantifying our belief in the possible outcomes of a future event. Okay? So, okay. So for an example of this, let's imagine that we have an event. And the event here is going to be our first event. So we'll say event 1. Okay? And the event 1 is going to be the first roll of a 6-sided die. Okay? And I'm going to call this event DR1 for die roll 1. Okay? And so what I can say is I can say something like this. Well, if I say, and so part of this exercise is to get you acquainted with the notation that I'm going to be using for demonstrating this probability stuff. So I can say something like this. Well, if I say, what's the probability P of that die roll 1 equals 2, what would be the probability of that? So if we're expressing, quantifying our belief in the possible outcome of a future event, what's the probability that this die roll that I have is going to have an outcome of 2?
1/6.
Yeah, 1/6, right? Pretty obvious. Okay? Now, it turns out that, okay, and I can also write something like, I'm not sure how big to write. I don't have as much. I'd like even more boardroom than is here, but this is okay. So I can also say, well, what's the probability that die roll 1 equals, say, something else like 5, right? So what's that probability? Yeah, it's also 1/6, okay? Okay. Now, there's something that's really important, and this is something that we're going to be using throughout this sort of logical lecture. And it's this concept of events that are independent, okay? So, independent events. So my question is what does it mean when two events are considered independent?
Probability of the one doesn't belong to the other.
Yeah, so the outcome of one event doesn't influence the outcome of the second event, okay? If that's the case, then these two events are independent, right? So basically, okay, so how do I write that, sort of mathematically? How do I represent that like this? Well, let's imagine that we have another event, and this is going to be event 2. Okay? And event 2 is just the second roll of 6-sided die. And I'm going to call this DR2 for die roll 2. Okay? Now, if two events are independent, I can write something like this. So the probability that die roll 2 is equal to 3 given, okay? So when I draw a line like this, it means given roll 1 equals 5, well, what's the probability? So the question is here, what's the probability of my second event equaling 3 given a particular outcome of my first event? Yeah, so essentially what it is it's equal to just the probability that die roll 2 equals 3, right? So if die roll 2 equals, if this is the case, these are equal, the outcome of the first event is not influencing the outcome of the second event, okay? So this is 1/6, right? Okay. Now, okay. So it turns out that when you can find something called the joint probability of independent events. Okay, so if two events are independent, you can find what's called their joint probability. So okay, and the basic idea is this. Well, what if I ask you, what's the probability that die roll 1 is equal to 5? And, so I'm just writing that to represent and, okay? And die roll 1 equals 5.
1 out of 36.
Yeah, so it turns out, so this is, a rule that you would have learned a long time ago. If you see this and events are independent, you can find the joint probability by multiplying the probabilities of the individual events. Okay? So this is equal to the probability that die roll 1 equals 5 times the probability that die roll 2 equals, oops, I wanted this to be a 2, not a 5. Okay. Doesn't matter.
Is that die roll 2 though?
Yes, sorry, thank you. Okay. So this is just equal to 1/6 times 1/6, 1/36, right? Okay, the and rule. So what we're going to be going over is just a series of ands and ors. Okay? So I just want to, develop this a little bit. This is, again, probably some, how old do you think you were when you learned this? Oh, pretty young, right? Does anyone remember?
12, 6th grade.
Yeah, so sixth grade, something like that. Yeah, okay. Now, there's one other thing I want to discuss, and that's this business of mutually exclusive outcomes. Okay? So what does it mean for outcomes to be mutually exclusive? Yeah, so mutually exclusive outcomes are this, when one outcome happens, the other can't happen, another outcome can't happen at the same time. Okay? So when one outcome okay? So a single event can't have two outcomes. Can't have these two outcomes if these outcomes are mutually exclusive. Now, if outcomes are mutually exclusive, you can ask something like this. Well, what's the probability that die roll 1 is equal to 5 Or, so here instead of an and, here I have an or instead of an and up here, or die roll 1 is equal to a 4. So I'm essentially saying, okay, in my first event, what's the probability that I get this outcome or this other outcome, right? And now if those outcomes are mutually exclusive, what I can do is I can just add the probabilities. So it's the probability that die roll 1 is equal to 5 plus the probability that die roll 1 is equal to 4, which is equal to 1/6 plus 1/6. Sorry, it's kind of small. 2/6 or 1/3. Okay? You might not be able to see that, but I think you get the point. Okay? So what we're going to be talking about starting now, essentially, is just a series of ands and ors. We have to think about, well, what's the probability of something happening? Okay? And what's the probability of something happening? There's going to be some ands in there, there's going to be some ors in there. And this is going to be the framework that we're going to be using to calculate what are called genotype likelihoods. Okay? So any questions before we go on to the next step? Yes?
Would it be that for the definition of probability, sometimes instead of quantifying our belief in possible outcomes in the future, we're kind of quantifying our belief in a outcome that occurred in the past?
Yeah, so well, if we quantify our belief in a future outcome of some unknown thing, that can be applied to something in the past. So I'm not a probability theorist, so I don't think about these kinds of things, but I think it all makes sense. So just you know what I'm saying. Okay. So let's see. Okay, any other questions? All right. So this is a framework to actually estimate unknown parameters that are unknown. Okay? So this is extremely common and extremely useful. Right? I heard people talk about maximum likelihood for many years, and I thought, oh, it's some really complicated thing. I can't understand it. I'm not even going to try. But it turns out it's actually really simple, very, very logical. And it's an extremely powerful framework to estimate an unknown from data. Okay? So essentially, maximum likelihood okay. So first of all, what is a parameter? In the context of statistics. Okay? What is a parameter? Does anybody know? This gets at the question of what's the difference between a parameter and a statistic. But so what's a parameter is essentially this. So it's a true. Okay, so true as opposed to estimated. A true measure of an individual or population. Okay? So the basic idea is this. For example, a population has a true allele frequency. Right? There's a truth. Or an individual has a true genotype. Right? At some position in my genome, I have 2 copies, at least I hope I do, and I have a true genotype, right? But essentially what will happen is I will collect data and estimate this parameter. I'll try to figure out what my genotype is. And I might be extremely certain, but I also might not be that sure, depending on what kind of data I collect. The basic idea is that the parameter is a truth that we're trying to estimate using data. And this maximum likelihood framework is a way that the logical framework that we're using to try to unveil this truth, to try to understand the true parameter that we're trying to estimate. Okay? Does anyone have any questions about that? So, like an individual's true genotype. Oftentimes when we have next-gen data, we're estimating genotypes from these data, and we have very different degrees of confidence in the genotype. So we might call a genotype, but that doesn't mean it's the true genotype of that individual at that locus, right? There is some truth, though, and that truth is what we're trying to get at, okay? Now, does anyone, so maximum likelihood then is just a method. So what maximum likelihood is a method okay? So basically what maximum likelihood is, it's a method for estimating an unknown parameter from data and some sort of statistical model, some model that we're going to use that allows us to relate relate our data to some probability. Okay? So a mathematical relationship. Now, what are the steps of maximum likelihood? Okay, maximum likelihood steps. Does anybody have any questions? Okay. So what are the steps in maximum likelihood? Well, step one, what we need to do is we need to, determine a mathematical relationship between the parameter being estimated and the data that we're observing. Okay, it might seem complicated, but we're going to work through this, and you'll understand what I mean. But we need, basically, step one is building a model. So when we're determining this mathematical relationship between a parameter and the data, we're building a model. Okay, and that's the first step of this process of maximum likelihood estimation. Okay? Okay? Essentially, this is building a model. Just because it has the word model in there doesn't mean it's some really complex thing. Okay, so number two. Essentially, what we're then going to do is we're going to do this. If we develop this mathematical relationship and we have data, right? What we can do is we can assume a particular parameter value. So for example, I can say, let's say I have a particular SNP or a locus that I know is polymorphic. And if I assume that an individual had a particular genotype, say I had an AT polymorphism at a locus, and I could say, hey, let's assume this individual has a homozygous A genotype. What would be the probability of observing the data that I did given this individual had a homozygous A genotype? Okay? So the next step is calculate probability of observing data assuming okay? So calculate the probability of observing data assuming a particular parameter value. So for example, if I assume that an individual has a particular genotype, what would be the probability of the data that I generated? You know, say I had 3 sequencing reads and they had particular alleles. You know, what would be the probability of those data assuming an individual had a particular genotype, right? Another thing to think about is this, like, let's say I collected a bunch of genotypes from a population, right? I could also say something like this. Well, what would be the probability of collecting those genotypes that I did, assuming a particular allele frequency in the population? So for example, like, let's assume that an allele frequency in a population is 0.5, and I collect 10 genotypes, and they're all homozygous for one allele. Well, what would be the probability of collecting 10 homozygous genotypes if I was assuming that the frequency of the allele was 0.5? Well, it'd be very low, right? It's unlikely to collect 10 homozygous genotypes in a population, 10 homozygous genotypes for the same allele in a population, if the allele frequency in that population was 0.5, right? So basically that. And so what's the third step? Well, the third step, it's getting kind of low, so there's probably no point for me to write it there. So I'll just go over here. Okay. Okay, so the third step is to just repeat step 2, but to do it for a whole bunch of different parameter values, or all the possible parameter values. Okay? So for example, if I had a particular locus that was polymorphic, let's say an AT polymorphism, well, there's 3 possible genotypes: homozygous A, heterozygous, or homozygous T. And for each of those, I could calculate, well, what's the probability of the data I observed given that the individual is homozygous A? What's the probability of the data I observed given that the individual was homozygous or heterozygous? What's the probability of the data I observed given the individual is homozygous T, right? So if I have this mathematical relationship between the parameter value and the data, I can calculate a probability of observing the data for many or all of the different possible parameter values. Okay? We're going to actually do this in a second. I just want to set up the logical framework before we go through and actually do this for considering next-gen data and possible genotypes. Okay? So basically, the next step, step 4, is this. You know, the best, once we do this calculation, once we have these probabilities of observing data, given all the different parameter values, our best parameter estimate is a value that maximizes the probability. So for example, let's say I have data, and I calculate, well, what's the probability of my data given an individual's homozygous A? And it's reasonable, it's not that low. But then I calculate, well, what's the probability of my data given an individual is heterozygous or homozygous for the other genotype? And they're both extremely low. Well, I'm pretty confident, it would be extremely difficult to have the data I did given an individual was either heterozygous or homozygous T. So I become pretty confident that the individual is homozygous A by comparing the probabilities of observing the data I observed given different parameter values. Okay, so we'll go through and do that. But the idea is that the best the best parameter estimate is value okay? The best parameter estimate is a value that maximizes the probability of the data. Okay? And so what you can say, and what I want to say just quickly, is you'll hear something like this. Well, what's the likelihood of genotype AA? What's the likelihood of genotype AT? What's the likelihood of genotype TT? Okay? And so basically, the likelihood that my parameter equals X, so for example, the parameter I'm trying to estimate is a genotype of a particular individual. The genotype of a particular individual equals something like homozygous A. So the likelihood that the genotype of individual is homozygous A is equal to the probability of the data given the parameter is equal to X. Okay? So this is just two ways to think about it. I prefer to use this. What's the probability of the data given a particular parameter value? But you'll often hear people talking just about likelihoods, genotype likelihoods. But what that just means is it means what's the probability of the data given a particular parameter value. Okay? So this all probably seems confusing, but to sort of demystify this, we're just going to go through an example of saying, here's our data. Let's use some logic, and let's use the and the or rule to try to calculate some likelihoods. Okay? Okay. So calculating and calculating genotype likelihoods. So, first of all, if we're going to calculate a likelihood, we're going to calculate the probability of the data, we have to define what's the parameter that we're trying to estimate, right? And so in this example, our parameter that we're trying to estimate is, let's say, the genotype of some individual, let's just call it individual 01 at chromosome 16, position 18,716, and let's say that there we know we have a CG SNP. Okay? So the parameter that we're trying to estimate is the genotype of an individual, of a particular individual, at a particular position in the genome. Okay? So we're trying to estimate this individual's genotype at one position in the genome. Right? If we have next-gen data, we're probably interested in estimating this individual's genotype at many different positions in the genome, but we do each one independently. Okay? So we're going through and we're going to do this calculation, but you can imagine just going to another site and doing the same thing for another site, and so on and so forth, and doing these calculations for the whole genome, if we have whole genome data, for example. Right? So, well, what's our data? Right? That's our parameter, but what's our data? Well, to start off simple, let's say that our data, we don't have very much data. Yes?
So is the CG SNP a conditional probability? What's that extra bit you added on there?
I'm just saying that we're going to assume here for the purpose of this, oftentimes we won't know what sites are polymorphic and these kinds of things, but for simplicity, we're just going to say that what I'm basically doing is defining my parameter space. By saying this is a CG SNP, I'm saying the only possible parameter values are homozygous C, heterozygous, or homozygous G.
So that's known information from other.
Yeah, known information from something else. Okay, but this is something that we would have to define too, and we can use a similar probabilistic framework to define what's a polymorphism first. Okay. So basically, so again, what this is telling me is that my parameter space, my possible parameter values are homozygous C, heterozygous, or homozygous G. Okay? Now, let's see, where was I at? Okay, so my data is this. I don't have very much data, right? Let's say that I just have one C read. Okay? And by one C read, I mean I just have a sequencing read that is from that position in the genome, that the one particular base that's polymorphic has a C in that sequencing read. Okay? Does everybody understand what this data is here? Okay. Now, we all know that, although sequencing is incredible, I mean, I just love next generation sequencing. It's so awesome compared to doing things before it was there. But it's not perfect, right? You can't, if you have a sequence, you don't have perfect certainty in this C, right? You don't know for sure that that was actually a C or it was a sequencing error, right? So we need to calculate the probability of observing this data, given particular genotype values. We need to know what the sequencing error rate is, okay? So what we're going to do is we're just going to say, for all these examples, we're going to say that the sequencing error rate equals 3%. Okay? So this particular base in our sequence read had a 3% chance of being an error. Otherwise, it was 97% chance of being correct. Okay? So basically, now that we've defined this, I want to talk about, well, what are the possible parameter values? Okay? So the possible parameter values, right? You could say, well, the possible parameter values are all the possible bases. But to simplify these calculations, let's just assume that the parameter space is either homozygous C. This individual can have a genotype equal to homozygous C, a genotype equal to heterozygous CG, or a genotype equal to GG. Okay? So this is my parameter space. Okay. So if we're going to do I want to do maximum likelihood here. Yes?
To try to understand, you include the possibility of CG and GG because you have that 3% sequence error rate?
Well, no. I mean, let's think about this. Yeah, so if I know this is a SNP, I know these individuals could be, without my data, these are the possible genotypes that the individual could be. Now, given my data, so what's the probability of observing one C read given this was the parameter, given this was the truth? Well, it's pretty low. If the individual is a homozygous G, it's pretty low that I'm going to get pretty low probability. But there's some chance of that happening because sequencing has an error rate. Okay? But already, without doing any math, we can say, well, the individual is probably either homozygous C or heterozygous. But how confident are we that it's homozygous C versus heterozygous? What is the, basically if I want to quantify, so first of all, I'm going to be uncertain here. I'm not going to have complete confidence, very strong confidence of one thing or the other, but am I 50-50 on this? Do I lean towards this? Can I quantify my belief in the individual's parameter, in the individual's actual genotype? Okay? Yes?
Oh, sorry, it was a different topic. I was just wondering, to double check yourself, should that step 3, the summation there, always be 1?
No, it shouldn't, which we'll get to.
Okay, sorry.
Okay? Which is, we'll get to that. It's a very, seems like it should because probability should always equal 1, but no, it shouldn't. Okay, and we'll get to why that is. Okay, so if we want to do maximum likelihood, I want to know, well, what's the likelihood that the genotype equals CC? In other words, what's the probability of our data given genotype equals CC? I want to know what's the likelihood that genotype equals CG. Well, it's equal to the probability of our data given genotype equals CG, right? And I also want to know what's the likelihood that genotype equals GG, which is equal to the probability of the data given genotype equals GG. So we're going to go through and we're going to do these 3 calculations. Okay? We're going to calculate genotype likelihood. What's the likelihood of this genotype? What's the likelihood of this genotype? What's the likelihood of this genotype? So what's the probability of our data assuming the genotype, and do this calculation for each of the 3 genotypes, and then compare the outcome and try to see what does that tell us about our confidence in the particular genotypes. Okay? So now let's start with just one of these. We're going to start with maybe the slightly more complicated one. But what's the probability of this C read given the genotype equals what's heterozygous? Okay? So if an individual had a heterozygous genotype, what are the possible ways we could have got a C read from that?
Do you consider position here, like CG or GC?
You don't need to. You could. You can either think about it like that or not. It doesn't matter. Okay, so is there one way that you could get a C, or is there 2 ways that you could get a C? What are the series of ands and ors? What I'm looking for here is the ands and the ors that are going to could produce a C read.
Are you doing it out of 4? So you're saying like a C out of ATCG for one chromosome and then the other? Like 116?
No, that's not the way we could do that, but that's what we're doing is we're calculating what's the probability of observing a C read given that this was the truth.
Oh,
so
okay.
the individual had a heterozygous genotype, had a genotype had 1 C allele and 1 G allele. Now, if that's the case, if this is the case, what's the probability of getting a single C read? There's a lot of people throwing a lot of different things out there. So what has to happen? It's a series of ands and ors. We need to break it down into ands and ors. Yes? She had a question in front of you too. You're exactly right, but
I was just saying the probability of getting a C or the probability.
well, what can happen is you can there's 2 ways it can happen. You can get a C, so you can sample the C allele and have no sequencing error, right? Or you can sample the G allele and have a sequencing error that converts the G to a C. Okay, so let's write those down, right? So we can do 2 things. We can sample the C allele. And so what I mean is just the allele that got sequenced, that molecule that was sequenced originated from some molecule that was in this individual. Okay? And it either originated from this, if this individual was this was the individual's genotype, it had to either originate from a C allele or a G allele, right? So what has to happen? Well, we have to sample the C allele and have no error, right? Or we have to sample the G allele and have a G to C error. Okay? So we have some ands here, we have some ors here. So now let's think about what's the probability of each event. So what's the probability that we're going to sample a C allele?
Frequency? The frequency?
Well, what's the frequency of the C allele in this individual? So again, here you have to realize that these probabilities that we're calculating, these likelihoods, are given. We're trying to calculate what's the probability of this data given this was the individual genotype. So if we assume that the individual had a CG genotype, what's the probability of sampling a C allele? Yeah, so it's 0.5. Now, what's the probability that there's no error? 0.97. 0.97. Okay? Now, I have an and here, so I can multiply these to get the joint probability, but what does that assume? Yeah, so it assumes that what allele I sample doesn't influence my sequencing error rate. Now, that's probably not completely true, right? So some bases are probably more likely to have errors than others, but for a relatively simple model, so our model here, by saying that these are independent, so putting a multiplication sign here, saying these are independent, means that we're assuming that there's no differences in sequencing error rate between the different bases. Okay, so it's a relatively simple, but I think it's actually quite a reasonable assumption, for example, with Illumina data. Okay? Now, what's the probability that we're going to sample a G allele? 0.5. Okay? And what is the probability that we're going to have a G to C error? No. Good guess. Yeah, so there's actually two things. We have a nested and here. There's two things that have to happen to get a G to C error. We have to have a sequencing error. So the probability of a sequencing error is 0.03. But then the error has to go from a C to a G, or sorry, a G to a C instead of a G to an A or a G to a T. So, yes?
But didn't you define the parameter spaces given that you only have a C or a G?
Right.
No, that's in the sampling here, not in the sequencing. Okay? So basically, the total probability is this. I have finding the joint probability between these two events. I have an OR here, I have a plus. I'm also finding the probability of these events. So if I calculate that, essentially the probability of generating a C read, given this individual had this genotype, is 0.49. Okay? So if this individual had this genotype, right, and I generated a sequencing read off of it, there's a 49% chance it would have been a C. Okay? Okay, so we did steps 1 and 2 we've essentially now defined our model. Right? We didn't define our model ahead of time, we logically thought about it while we were just going through this example, but now we've defined our model. We've calculated the mathematical relationship for our data, assuming one particular parameter value, but now we have to do this for these two other possible parameter values. Okay, so we're going through and we're calculating the likelihood of each possible genotype. Okay, so the next ones are a little bit simpler. Okay, so here, well, what's the probability of a C read given the individual was homozygous C genotype? So what has to happen here?
Probability of C without error and probability of C with error. Do you have to consider both of those?
Well, if C had an error, we wouldn't be getting a C. So what has to happen here? We have to sample a C allele. You can just think about it in the same context of this. So sample a C allele and have no error.
Okay.
So what's the probability that we're going to sample a C allele? It's 1. And what's the probability that we're going to have no error?
97.
So this likelihood is 0.97. So they already don't add up to 1. Right? Okay. So what's the last thing that we have to do? Well, we need to calculate the likelihoods of the 3 possible genotypes. And then and then compare them. Okay? So let's say, well, what's the probability of a C read given genotype equals GG? Well, what has to happen to get a C read, assuming this was the individual's genotype? Yeah, you have to have an error. So we can, just to be consistent, we can write it like this. We have to sample the C allele, or sorry, a G allele, and have a G to C error. Okay, the probability of sampling a G allele is 1. The probability of having a G to C error is what?
1/3.
Yeah, 1/3. So 2 things have to happen. You have to have an error, which is 0.03, and that error has to be correct. So it has to go from a G to a C instead of a G to an A. So that's 1/3. With this 1/3 here, that's, again, assuming that all the sequencing errors are equally likely. It's reasonable. And when we do this, we get that 0.01. Okay? So we've done this now. So my question for you is, well, what's the most likely genotype? Yeah, but here's a question for you. What's the probability that the individual is actually a CC genotype, given the data?
That or that or that.
I'm going to flip this around in a second here. So let me do one more calculation. So here, we just did this for one. So I want to continue to define our model before we go into this concept of Bayes and posterior probabilities, okay? So here, we calculated these data, or sorry, these likelihoods with just one read. But what if we had multiple reads? What if we had 5 reads from the individual? Or 2 reads from the individual? Can we still calculate these, or does it become too complicated? Right? So let's go through and let's calculate. Let's assume we have a little bit more data and perform these calculations. Okay? And then we'll sort of think about how to evaluate the likelihoods that we calculate. Okay? Does anybody know what time it is? It's 9. Okay. Now let's say this. Let's say our data now is 2 C reads and the sequencing error rate still equal to 3%. Okay?
How do you use the make this error?
Well, the error rate is actually an estimate of the error rate. So I'm just here saying it's 3%. Does anyone know why I'm thinking 3%? It's very practical. Because if you divide 3 by 1/3, you know, okay. But it turns out that there's Illumina data. If you have any of you ever have FASTQ files? Your FASTQ file has a base call. It has 4 lines, right, per sequence read. One of those lines is a quality score line. So every single base, every single sequence read, and every single position of every single sequence read has a quality score. And that character can be converted to a probability very easily. Okay, so that character that you see, it's like a pound sign or a capital B or all sorts of weird stuff. That can be trivially converted into a probability that is an estimate of the error rate for that position. Okay? So if you were calculating this from real data, you would look at the error rate for that particular position, and that's how you would make the calculation. Okay? So, well, let's think about it here. So what's the probability of C reads given the individual had a homozygous C genotype? Yeah, so, well, what has to happen here? I have to get a C read. So just break down the math. Well, read 1 is C, and break down the logic, read 2 is C. Okay? So read 1 is C, and read 2 is C. Okay? Well, what's the probability that read 1 is C? And what's the probability that read 2 is C? Same thing. So if this event happened independently, or this happened on its own, we'd say this probability is this. Now, if I want to find the probability of this happening, can I just multiply these together? So this happening and the first event having an outcome of C, and the second event having an outcome of C? Yeah, so if these are independent, I can multiply these together, right? And so it turns out like the genotype calling software that we use will assume independence here, and it'll calculate this by going like this, right? Okay? But we need to keep that in mind. We need to keep in mind this is an assumption. We assumed independence here. We calculate this. So how could we calculate this likelihood here without assuming independence?
Covariance.
So if you calculated the covariance and then incorporated that, seems reasonable. But could you deconvolute the biology from the technology? Yeah, you go across multiple individuals. I haven't thought about that, but my point is it becomes complicated and it's not so clear. So assuming independence, I think is reasonable, but can anybody think of a situation where there wouldn't be independence? What? Yeah, so there's this problem in next-gen sequencing where you take a molecule and you duplicate that molecule many times, and then you sequence the duplicated molecule. So you have a whole bunch of reads, right? Let's say you have multiple C reads, but these reads originated from just one sampling event of the original genome, then were duplicated multiple times. So that means if you get one read, if you get one C read, you're more likely to get another C read if there's a presence of duplicates in the data set. So this likelihood here would not be accurate. Okay, so do you have duplicates? Do you not have duplicates? I don't know. But my point is that right here, we're assuming, in this calculation, we're assuming independence. And it's important to understand that we're assuming independence here. Okay? It's another assumption. So now we've completely built our model. And we have all these assumptions. We're assuming independence between the reads. We're assuming an equal error rate. What other assumptions are we making? We're assuming that the probability of the different errors are the same, right? This is sort of, we've defined this. Okay, so now what if let's go through and let's calculate, well, the probability of C reads given genotype equals is heterozygous. So here with maximum likelihood, we're going to go through and we're going to calculate the probability of our data, assuming a particular genotype, but then we're going to repeat this for the 3 different genotypes. Okay? And if we do this, well, what has to happen? Well, we have to get one C read and then another C read. Well, what's the probability of getting, I don't have this up anymore, but essentially the probability, this is equal to the probability of C read given genotype equals CG. times the probability of C read given genotype equals CG, which is equal to 0.49. Is that correct? That's what we determined before? Times 0.49. Okay? And so overall, this is equal to 0.24. Okay? So let's do one last calculation. Here we go. Okay. What's the probability of CC reads given genotype equals GG? Well, this is just equal to, the probability of C read given genotype equals GG squared, which is equal to 0.01 squared equal to 0.0001. Okay? So again here, what's the most likely genotype? Yeah, so the most likely genotype is CC, right? Because it's the one that maximizes the probability of our data. But how confident are we that it's CC? Seems like our data, it's not that unlikely, given that genotype was CG, right? So let me do one more example, and then we're going to sort of apply Bayes' logic to these data sets to make some, a little bit more intuitive understanding of these likelihoods. Okay, so here, now the calculations that we just made here, right? They weren't that complicated, but I want to make the point that we could do this now with any number of reads in any possible genotype. Okay? So for example, let's say we have even more data. Okay? And the more data is this. Let's say let's say our data is this. C, C, G, C. Oops. Reads given genotype equals CC. Okay? So what has to happen to get these data if our genotype was this? Well, the first read has to be a C, the second read has to be a C, and the third read has to be a G, and the fourth read has to be a C. Essentially what we have here is we just have multiplying like this, 0.97 times 0.97 times 0.01 times 0.97 equals 0.0091. Okay? So this is the likelihood, this is the probability of these read data given this genotype. So this is the likelihood of this genotype in a situation where we have these data. Okay? And we could have done this calculation for the 3 different genotypes, and then we could compare those likelihoods, right? And here, my gut is that we'd say, okay, the most likely genotype is a heterozygous genotype, right? But can we actually quantify our confidence in the heterozygous genotype? Okay, so what I want to get at here is, let me just actually start to write it. Okay. I want to get into this business of Bayesian genotype calling. Okay? Now, what we did here is we just calculated likelihoods, right? So the likelihoods And we're going to go with the likelihoods here, which is equal to what's the probability of the data given a particular parameter. Our likelihoods that we're going to be working with for a little bit are this. What was the probability of C reads given genotype equals CC? 0.94. Someone correct me if I'm wrong on these. Probability of C reads. So our data here is if we had 2 reads and they were both a C. Okay? Okay, and last one. Okay. Now, we can calculate these likelihoods, right? We can say, well, I guess the homozygous C genotype is the most likely. But I look at these and, I'm not smart enough to be able to interpret them in a satisfying way. They don't sum to 1. And because they don't sum to 1, I can't tell you. See, I don't care. I don't care what's the probability of getting these data given this genotype. What I care is what's the probability of the genotype given the data. So I want to know what's the probability that this individual has a homozygous C genotype? What's the probability that this individual has a heterozygous genotype? What's the probability that this individual has a homozygous G genotype? Right? Those should sum to 1. To me, that's much more intuitive to be able to think about this. Essentially what I want to know is I want to know not what's the probability of the data given a parameter value. I want to know what's the probability of a parameter given the data. Right? I want to know what's the probability that this individual has a homozygous C genotype given my data. Right? Is this individual have a 75% chance of being homozygous C and a 25% chance of being heterozygous? Or is it a 50% chance, 50-50, 90-10? What is it? Right? I know this is probably really low, but what is it? Okay? Can people understand how much more logically satisfying this would be than these likelihoods? Right? But how do we get that? How do we calculate this? How do I calculate what's the probability of genotype CC given my data? Okay? Does anybody have any guesses? Can we just derive this on our own? What?
Positive results out of total positive.
I think what you're saying is this. If I want to calculate what's the probability of genotype equals CC given C reads, are you telling me to do this? Actually, let me move this over just a hair. Okay, so what if we just go through and let's say we do this. Okay? Now, to me, this is extremely satisfying here. Right? Now I'm saying, well, I'm almost 80% sure the individual is this genotype. Just over 20% sure here. And here, there's very, very low probabilities. I call it 0 because it's like 0.0000. A lot of zeros. And then a 1 or something low. Okay? Now, but the question is, so this seems very satisfying, right?
Logically.
Doesn't seem it seems unsatisfying to some people, satisfying to others. Well, to me, it seems really satisfying.
It's missing the prior probability.
Yeah, so if you know Bayes' theorem, you realize it's not perfect. It is actually an application of Bayes' theorem, but we made many assumptions here. Okay? So this is Bayes' theorem here that we just applied in a completely legitimate way. It's that simple. So for many years, I just think this is so funny. For me personally, for many years, I heard the word Bayesian, and I just thought it was like this really complicated thing. And I was like, there's no way I could ever comprehend Bayesian probability. It's like so complicated. But actually, we just did it here like naively. It's actually quite simple. Okay? But let me give you this example to say that this is, although this seems good, it seems very logically sound and very intuitive, there are problems with it. Okay. Now, let's say that this individual came from a population. So, this individual, 01, came from population X. Okay, so this individual that we sampled here was from a particular population, right? And we knew something about this population. So let's say that we knew that the frequency in population X of the C allele, okay, was 0.1. And the frequency of the G allele was 0.9. And, let's just say we also knew this locus was in Hardy-Weinberg equilibrium. So let's say that in this population, the frequency of the CC genotype was 0.1 squared equals 0.01. The frequency of the heterozygous genotype equal 2PQ and the frequency of the homozygous G genotype was 0.9 squared equals 0.81. Okay? Now, how does this... So let's say that this was the case. So this individual came from a population with these genotype frequencies. Now, forget about any math here, and let's rethink about the likelihoods that we calculated. So the likelihood of this, of the data given this genotype was this, and this, and this. But without doing the math and just thinking about it now, if we reevaluated these likelihoods in the context of this, what would our gut be? Would we still think this individual is most likely to be homozygous C? Because we would think that, homozygous C genotypes are extremely rare in this population. We're actually 18 times more likely for this individual to be a heterozygote, right? And so now it makes me think, well, I wasn't really that much more confident in a homozygous C over a heterozygous, and heterozygous is so much more likely that now I'm thinking, well, that individual is actually probably a heterozygote, not a homozygous C. Right? I'm more inclined to think that that individual was a heterozygote. Okay? But how confident am I that this individual is a heterozygote? How do I quantify my belief that this individual is a heterozygote versus a homozygous C versus a homozygous G? Yeah, so essentially now we actually apply Bayes' theorem, which is this. Okay. So the basic idea is this. Okay? The probability of a particular parameter value, I'm going to call it K, given the data. So, for example, the probability of genotype CC, given our data, is equal to the probability of our data given that particular genotype times the probability of that parameter value over okay? So what in here do we recognize? So what is this? Yeah, this is a likelihood. So the probability of data given a particular parameter value. This is a likelihood. Okay? This is what's called a posterior probability. Okay? This is also likelihood. But what is this? Yeah, these are what are called priors. Okay? So prior. Okay? So now let's think about the calculations we did there in this context here. Okay? So essentially what I'm saying is this is the product of the likelihood times the prior. This is the product of the likelihood times the prior, but then I'm summing all the possible parameter values from 1 to n. Okay? The sum of all the likelihood times the prior for all the possible parameter values. Okay? So how does this compare to what we did? Okay, well, what were our likelihoods? Likelihoods were probability of data given genotype equals CC 0.94, probability of data given genotype equals CG 0.24, probability of data given genotype equals GG equals 0.0001. Okay, well, what are our priors?
The genotypic frequencies.
Well, it depends. So let's say that we don't know. We're completely naive. We can come up with what are called uniform priors. And so let's say that the probability of this genotype is 1/3, the probability of this genotype is 1/3, and the probability of this genotype is 1/3. Right? Okay? But we could also come up with a different set of priors. So let's call these like allele frequency and Hardy-Weinberg equilibrium. Right? So those priors told us this. Sorry, let me write this really quick, actually, just to clarify. The priors are the probability genotype equals CC is equal to 1/3. probability of genotype equals CG is equal to 1/3. Probability of genotype equals GG is equal to 1/3. Okay? And so, but if we were considering allele frequency, the priors would be this, 0.01, 0.18, 0.81. Okay? Now let's do these calculations. Now we've defined our likelihoods and priors. So let's perform the calculations using Bayes' theorem. Okay? So if we say, well, what's the probability of genotype equals CC, given our data, well, it's equal to 0.94. So this likelihood right here times the prior here over 0.94, 0.24, 0.0001. And if we do that, well, we can actually see that these cancel out, and we get 0.797. Okay? So we actually got the same result. So this naive thing that we did of just taking the likelihoods and summing them up and putting them as the denominator, and then taking a single likelihood on the numerator, we actually just were applying this theorem, but we were applying it with two important assumptions. What are the two assumptions? Well, we have all the assumptions in the model that we use to calculate the likelihoods. All those assumptions are still true, but then we have a couple assumptions that we added on here when we applied this. So one of the assumptions is that we have these uniform priors, so that the genotypes are equally likely. We're applying, if we just, in that naive calculation that we did that calculation, but essentially Bayes' theorem is apparently true. It's like, there's no question it's true. It's proven, I believe. I don't really know anything about it, but it's true. But we all of a sudden added an assumption here of equal, this uniform priors, so equal probability of these three different genotypes. But what's the other assumption that we added? We kind of talked about this a little bit. But essentially the assumption here is that we completed the three genotypes are our complete parameter space. Okay? Now when we're calculating the likelihoods, we could calculate those likelihoods and the math there would be legitimate regardless if other genotypes were possible. So for example, like let's say a third genotype, this was a triallele. Okay? So, but those are two important things to consider here. Now, we can go through and we can calculate this for the other three genotypes using the same uniform priors, and we get the same results as we did before, right? So, assuming the uniform priors, assuming equal probability of the three genotypes, and assuming that these are the only three possible genotypes, we're now, 80% confident in this genotype and 20% confident in the heterozygous genotype, right? But we have more information now, so let's say that we actually know the allele frequencies in that population, right? So let's apply this same logic here, but now using these priors, because we know that information. That's additional information that we have, right? So if we do this calculation, I want to calculate what's the probability of genotype CC given data And now we're going to do this calculation assuming these allele frequency priors and Hardy-Weinberg equilibrium, right? So now what is it? Well, it's 0.94 times 0.01 over 0.94, 0.01 plus 0.24, 0.18 plus 0.0001 times 0.81. And if we do this, we get 0.178. And if we go through and probability of genotype equals CG, given data, equals 0.820. Probability of genotype equals GG, given data, equals 0.002. So what does this tell us? Okay, what does this tell us? Someone has to say something. Yeah, so now we're 82% sure. So, well, this tells us a number of things. It tells us that our confidence in the different genotypes could be all over the place depending on what we're assuming, right? So we went from being pretty confident in one genotype to being pretty confident in a different genotype with the same data. So one important thing here is that, yes? Yeah, so we don't, that's a great question. Say our allele frequency estimates are very poor. If the allele frequency estimates are very poor, then here, right? But if we're, okay, so what about, is a uniform prior bad? Well, if we were just going to evaluate the likelihoods, so that 0.94, 0.24, whatever, 0, the relative proportions of the likelihoods is no different than the relative proportions of the posteriors, or the relative values of the posteriors is the same as the relative values of the likelihoods, right? It's just normalized so they sum to 1, so it's more intuitive. So certainly applying Bayes' theorem with a uniform prior is not, in my mind, I'm not a statistician, but it's not really any different than evaluating likelihoods. But we are making that assumption that we're completely examining the parameter space, which is good to keep that in mind. But using these priors, well, here's a really important thing I want to get at, is that a lot of people think that they use Bayesian approaches, and they use a software package that implements a Bayesian approach. And they put in priors, and they think like, well, I'm putting in these priors, that's what I think, I'm just going to put these in. I mean, that's fine, but you have to realize here that your priors have equal weight as your likelihoods, or, as your likelihoods, right? So priors have a huge influence on the posteriors. They have just as much influence on the posteriors as the likelihoods, right? So people tend to think they put in priors, and it's going to influence something a little bit, but not that much, maybe. But that's not the case. I mean, priors have a huge influence. And so one thing that can happen, for example, is let's say our likelihoods were very similar. So let's say our data just couldn't distinguish between the possible parameter values, such that our likelihoods were 1/3, 1/3, 1/3. Well, our posteriors are then just going to depend on our priors and not our data at all. Okay, so that's another good thing to keep in mind, right? So, I think if you're applying Bayesian approaches, it's not some rocket science thing like I thought it was for many years. But you have to sort of understand the math here so that you can have an idea of what's going on. Yeah.
So this brings up a question that's always puzzled me. So if you're really, really confident in your priors and they're really bulletproof, and your data completely collide with them, then do you assume that it's the model that's wrong? Or?
So we have this, we're doing this work on this thing called devil's hole pupfish. And without getting into the details, this paper was published recently And basically, I think they came to the very wrong conclusions. They used a Bayesian approach. They used an approach called ABC, approximate Bayesian computation. And if you read it carefully, their priors never sunk up with their data, and it would never, all their summary statistics would never sync up with their simulations, you know? And their priors ultimately dominated, and they published this paper. But we came to very different conclusions, and we're like, how can we come to such different conclusions? We kind of dig in. You know, it's hard to figure out exactly what people did in these papers, right? It's complicated. But I'm pretty sure that, you know, we'll see what peer review says, but that's my opinion of what happened. I trust our data. We have much, much stronger, much more data, for example, on this issue. Yeah?
Are priors limited to population level data?
I mean, you can use whatever you want for priors.
Like for the, okay.
But for genotyping, it seems like a reasonable, it'd be probably better to use genotypes. You could measure, you could estimate allele frequencies, and then you could use this Hardy-Weinberg assumption to calculate genotype frequencies. You know, but if you had directly genotype frequencies. So anyway, we're going to go through and we're actually going to use some software that implements this kind of thing, and we're going to compare the posteriors that come out depending on, you know, uniform priors, an allele frequency prior, right? So it turns out with next-gen data, if you have a whole bunch of individuals genotyped, and each one has, say, 1x coverage or 2x coverage, well, your likelihoods aren't going to be able to distinguish very strongly a particular individual's genotype, right? But if you pool all your data from all the individuals, you can actually take all the data and estimate allele frequencies in the population from just 2 reads in each individual without actually calling genotype. So normally when you say, I'm going to estimate an allele frequency in a population, you would genotype individuals and then use the genotypes to estimate allele frequency. Right? But with next-gen data, you can actually estimate allele frequency directly from the raw data without calling genotypes first. And then you can use that as a prior to add for your genotype calling to calculate posteriors, right? So, and that's one way to improve the information content with low coverage data. But it has a lot of assumptions, and understanding those assumptions is really important, okay? So does anybody, so this is all I wanted to show. So let's take a, like a 5-minute, just a really quick break so I can turn on my computer and stuff, and we're gonna go through now, and actually instead of doing these calculations by hand, we're gonna run some software that just does the calculations, okay?